8.1 Add and subtract polynomials. Let's first revisit the word monomial. Any number is considered a monomial. So 10 would be an example. Any variable, one-term variable, will be also considered a monomial. The product of a number and a variable or variables is also considered a monomial. So half times a times b squared. Variables with whole number exponents is also considered a monomial. Okay, let's look at examples when it's not a monomial. You have 5 plus x. This is not a monomial because we have a sum. And for the next one, 2 over n, you cannot have a variable in the denominator. And for the next example, 4 to the a power, this is not a monomial because you have a variable exponent. So you cannot have a variable exponent. And for the next one, you cannot have a negative exponent. It must be a whole number exponent in order for this to be a monomial, as we see here. Okay, let's look at the word degree of a monomial. This just means the sum of exponents. So if we look at the number 10 here, the exponent is 0 because 10 to the 0 power is 1. Then the degree of this monomial is just 0. And the exponent of the variable x is 1. So we only have 1 as the degree of the monomial. And for the next one, the variable a has an exponent of 1. The variable b has an exponent of 2. So if we take 1 and we add 2, we get 3 as the degree of this monomial. And for the next example, 5 will be the degree of the monomial. Okay, now let's look at the word polynomial. Polynomial just means a monomial or a sum of monomials. Each called a term. So let's look at an example of a polynomial. 2x cubed plus x squared minus 5x plus 12. Now we have a couple vocab terms here. The leading coefficient is the coefficient of the first term when a polynomial is written with exponents decreasing from left to right. So 2 here would be your leading coefficient. And the degree of this polynomial will be the greatest degree of its terms. So that would be the 3. And then we have the constant term, which is just the number positive 12. Now, a binomial is a polynomial with 2 terms, such as 2x minus 5. A trinomial has 3 terms. So tri means 3, bi means 2. And terms are just all of these separate components that make up the polynomial. And like terms are terms that have the same variable with the same exponent. For example, 5x and 6x. So I'll list the terms: 2x cubed, x squared, negative 5x, and positive 12. And these are just random examples. Guided practice. Write the polynomial so that the exponents decrease from left to right. Identify the degree and the leading coefficient of the polynomial. So here, when I look at this polynomial, I see that 4 has the greatest exponent. So I'm going to write 4y to the 4th power, and then I'm going to add it to 6y cubed, and I'm going to subtract minus 2y squared, and then minus 5. As you can see, now I have the exponents in decreasing order. So according to our definition earlier, the leading coefficient is the coefficient of the first term when the polynomial is written with exponents from left to right. So 4 would be the leading coefficient, and the exponent here of 4y to the 4th power would be the degree. Okay, the greatest degree of its terms. Okay, now, the bottom here is it wants you to tell whether the expression is a polynomial. If it is a polynomial, find its degree and classify it. So for the first example here, we have 7b c cubed plus 4b to the 4th power c. So is this a polynomial? I would say yes. Okay, and why? Because it doesn't have a negative exponent or a variable in the denominator. Okay, and the degree, you would take this term, 4b to the 4th power c, and add the exponents. So that would be 0 plus 4 plus 1. And you would get 5. And 5 is greater than 3 plus 1 plus 0, which is 4. Okay, so that's the reason. And because there are 2 terms, we will classify this as a binomial. And for the next example, I will also say this is a polynomial There are no negative exponents. Okay, it satisfies the definition. Now, if we look at all its terms, it seems like we can reorder these terms. So negative n cubed minus 6n squared plus 4. So 3 is the greatest degree. So we write 3. And for the next example, we have negative exponents. So this is not a polynomial. So we don't have to do anything. And the number 7 is a polynomial. Yes, it's a one-term polynomial. And more specifically, it's a monomial. We classify it as a monomial. And let me backtrack a little bit. Because this second example here has 3 terms, we call this a trinomial. Okay, so binomial, trinomial, monomial. And for this case, it's 7 to the 0 power, so 0 will be your degree. And for the next set of practice, we're going to look at how to find the sum or difference of polynomials. So if we look at this first example here, we need to first distribute the -1 into this binomial. So let's copy 6c squared plus 3c plus 9, and then -1 times 3c is -3c. -1 times -5 is +5. Now we can cancel out +3c and -3c, and we're left with 6c squared plus 9 plus 5. So I could add these together to get plus 14. And thus, this is simplified. And we look at the next example. Again, I need to distribute the -1 into this trinomial. I'll recopy the first trinomial, 4d minus 6d cubed plus 3d squared minus 9d cubed minus 7d plus 2. Okay, and then now we need to rearrange these terms so that we can add them. So minus 6d cubed minus 9d cubed will give you minus 15d cubed. And then we have positive 3d squared. We don't have any other terms with d squared, so we just recopy that. And for d, I see that I have a minus 7d, which I can add together. So 4 minus 7 is -3d, and the constant positive 2 stands alone. So in this case, this would be my simplified solution. And now let's look at this one. Here it's positive, so we don't have to worry about distributing. So 3r squared s plus 5rs plus 3 minus 8r s squared minus 9rs minus 12. Now let's find the like terms. We have positive 5rs and then minus 9rs. And then 3r squared s is alone, negative 8rs squared is also alone, and we also have 2 constant terms in which we can combine together. So I'm going to first write 3r squared s, and I'm going to take negative 8rs squared and combine it with 3r squared s. And then I'm going to add 5rs to negative 9rs, which makes negative 4rs. And then I will add 3 and negative 12 to get negative 9. This will be our simplified expression. And for this next problem, we have 5mn plus 3m minus 9n, and here we need to distribute the negative 1 into the binomial to the right. So that would be negative 13mn, and then negative positive makes negative 2m. And now we have to combine like terms. So plus 5n can be combined with negative 13mn. So that would be negative 8mn. And the next one will be positive 3m with negative 2n. So that will make 3 minus 2 makes positive m. And we have a leftover of negative 9n. And that would be our simplified expression. And for this next problem, we are to find the area of the floor plan to the left. Okay, first I'm going to write an expression for this big rectangle here. And this would make 4x times x, which equals 4x squared. And this little square will be x over 2 squared, which makes x squared over 4. And this little rectangle here makes 8x minus 32. And now I'm going to combine all of these terms to make one polynomial. So 4x squared plus x squared over 4 plus 8x minus 32. Now we can still combine these two terms. So I'm going to rewrite 4 as 16 over 4 and continue to simplify. So this would be 17 over 4x squared plus 8x minus 32. Word problems. In 1997, the median sale price for a one-family home in the Northeast was about $187,443, and the median sale price for one family in the Midwest was about $151,629. From 1997 through 2003, which is a period of 6 years, the median sale price for a one-family home in the Northeast increased by about $13,857 per year. So this is the rate of increase for the Northeast. And the median sale price for the other family in the Midwest increased by about $5,457 per year. So this is the rate of increase for the Midwest. So in the first part, you need to write two equations that model the median sale prices of a one-family home in the Northeast and Midwest as functions of number of years since 1997. So for Northwest, we began with $187,443 in 1997. And the rate of increase is $13,857 per year. So I would add that to 13,857 times T. And the same would go with the Midwest, $151,629 in 1997. And then we would add that to the rate of 5,457 per year times T. Now, the next question is, how much more did a home in Northeast cost than a home in the Midwest in 1997 and 2003? So in 1997, the time would be 0. So I need to take the expressions here and subtract them. So n subtract m. So here I already have the work shown for you. I took 187,443 plus 13,857t, and then I subtracted the binomial 151,629 plus 5,457t. And notice that I put parentheses around the second binomial. And now I just need to substitute in 0 for t. And these two terms are canceled out. So you end up with 187,443, and you will subtract 151,629 to get $35,814. And for 2003, the time will be 6 years. So in this case, we will substitute 6 in, and we will get $86,214. And the next part of the question is to find the change in sale price of each area between the 6 years. So again, I need to take this expression, substitute 6 in, and then subtract the same expression again with brackets around it, and I need to substitute a period of 0 years. And I will do the same thing for the Midwest. Take the second equation, 151,629 plus 5,457 times a period of 6 years. And after I find this amount, I need to subtract the same equation again, with the exception that this time you need to multiply by a period of 0 years, because we're looking for the change in sale price. So after you do all the calculation, these are the answers that you should get. And this concludes our lesson.